Once again, the rock physics, the modeling, seismic modeling inversion, and seismic well ties. So, what are we going to do in a rock physics model? Kind of things that we would really focus in on for these three types of rocks: the pressure effect, especially both isotropic stresses and anisotropic stresses effect on the shales and tight gas sands and carbonates. Matrix modulus, the influence of different materials, minerals. We all know the shales are not just shales, and carbonates can be a mixture of various things in there. Pore geometry, okay. The effects, we know that we need to get away from just a spherical pore geometry, one single porosity type models, but once you introduce pore geometry, what are these effects on velocities and fluid substitution? And this part actually, I'll talk a little bit more about it. Resistivity, can we use resistivity to constrain our models? Okay. We have resistivity law downhole, and especially now that rock soil images is part of OHM, and OHM is focused on the EM side of the business. So we're looking at the EM response and see how it can help us constrain some of our rock models. It's a natural thing to do. In shales, especially, and also in tight gas and other places, a lot of times we're looking at fractures. What are the effective fractures of the seismic anisotropy on anisotropy observed in the well logs? How do we quantify it? If we have more fractures one direction or another, how does that affect our seismic response? Really what we want to do is look at models with additional complexity to address these issues, but we're living in the real world. We want these models to be constrained by measurable parameters, okay? And that's why one of the things that we want to do is looking at resistivity log and see whether we can have to constrain some of the parameters. We are going to perhaps take some advantage of my background in acoustic logging and see how we can use various parameters measurable from acoustic logs to help us constrain our rock model. Okay, so this is Ted's famous picture. The tight gas example just really focus on one thing. These bunch of wells, this is a velocity porosity cross plot, but if you project this bunch of wells back to zero porosity, the intercept is not a matrix. Something is happening. We can use various model on it, and which is the best model to use in these situations. I don't think there is a consensus yet. We're trying to look at how best to model this type of behavior, right? Carbonates. The thing about carbonates is it's really a complex microstructure. And in something like this, you have connected porosity with different grain size and shape, but the fluids can flow between the pores. But sometimes you get things isolated pores, and fluids are not flowing between them. You know, how do you distinguish this type of rocks and how do you model them properly? So, and this is a similar plot that to what I showed before on tight gas. This porosity, velocity cross plot on carbonates. Now, on here we actually plotted on it various DEM curves or differential effective media, or different pore shapes of different aspect ratio, 0.01, 0.03, 0.1, 0.3. So, and this is a carbonate well. Two things. One, you can see that this block doesn't lie on the aspect ratio alpha equal to 1, which means they don't lie on spherical pores. Okay, pores are not purely spherical. The other one, it's just the same as tight gas case, that these, when you project back to zero porosity, once again, don't come up to the matrix that something else is happening. But you see this distribution, and you just take a look at it, and you notice that one single aspect ratio probably is not the right answer, because it's actually spread out over various different aspect ratios. So these are the complexity we want to look at and see what is the best thing we can do to model this. So now, as I said, I'm going to talk a little bit about pore shape, effect on velocities. This is something that a long time ago, but that's anyway. So with different pore shapes, the idea I would strive to use is for these cracks, a little bit of a crack goes a long way. So adding tiny bits of cracks, it really changes the properties. And when you have gas saturation, which is the red line, it actually changes even more. So it's very sensitive to fluid substitution, and a little bit of these cracks actually change your modulus and velocity behavior quite a bit. So yes, we need to start adding in these layer complexity, but we have to be careful and learn how to use it and have constrain it, because otherwise we'll get the wrong answer. Okay. So care needs to be taken when you're doing fluid substitution, when you start adding in this kind of cracks. So this one example from Franklin Ruiz. Franklin here? Anyway, so one of Gary's recent graduates now at Roxor Images, and he basically used the P wave and inverted using I think he used DEM or in this one to predict the shear wave resulting fitting using a single aspect ratio varying. So and it actually predicts the shear wave pretty well in this particular case. So initially, this kind of procedure intuitively makes sense, but we need to really refine it and figure out where it works and where it doesn't work, and especially, as I said, regarding fluid substitution in gas. Okay, this is another thing that people well known over the years, but we keep repeating. This is a pressure velocity versus pressure curve with water, benzene, and air dry samples. Pressure dependence is complex and really as a function of saturation. When looking at 4D type problems, changing stress problems, we have to keep in mind. There's no easy answers, but you have to realize you can see large changes just purely due to stresses. So, okay. Changing gear a little bit, we're going to look at, in this P3, we're going to look a little bit more, allele look and inversion is really the theme. We're going to look at anisotropy modeling inversion. We're going to try to think about some probabilistic inversion with uncertainty estimates. We're going to look at some offset angle transform. Subhashis will talk a bit more. This is highlighting global versus local algorithms, inversion of multiples, a question of span, and some of the roles played by supervised artificial neural nets in Fourier form inversion. And then obviously upscaling is always an issue. So I saw this slide from Subhashis. Really the idea is you can see the angle versus offset is not necessarily constant, and it really is a function of the kind of